The industry as a whole is looking to reduce power and BOM cost while increasing the optical throughput available on a typical faceplate. The answer is smaller, faster optics in the form of compact form factor pluggable 2 or CFP2 100 gig optical modules. Enabled by heterogeneous stacked silicon interconnect technology, or SSI, and the Xilinx 28 gigabit GTZ transceivers, the Virtex-7 H580T FPGA allows fast adoption of this new optical standard. Today, I'm going to show you the world's first all-programmable heterogeneous FPGA interfacing to a CFP2 optical module. We'll go through 4 steps required to bring up the system and then demonstrate how Xilinx simplifies the process. Before we begin getting these links up, let's take a look at the setup. Here we have a Xilinx VC750 board with a Virtex-7 H580T and dual Yamaichi CFP2 connectors and cage. In one of the slots, we have a Finisar CFP2 optical module connected to a 10-kilometer spool of single-mode fiber. We're going to walk through the 4 steps to bring up a fully operational link. 1. Generate an hybrid design via the Vivado design suite. 2. Enable the serial links in internal loopback. 3. Enable the serial links in external loopback with the CFP2 module in the path. And then finally, 4. Exercise and validate the system as a whole with payload data and an external tester. Generating an hybrid design in Vivado that reflects your design is very straightforward. We selected a 25.78125 gigabit per second line rate and a 1/80th clock running at 322.2 megahertz to mimic a 100 gig Ethernet Cowie4 interface, a common use case for these CFP2 optics. The tool will output a bit file that we can use immediately. Once iBert has finished implementing and we have configured the Virtex-7 device, we can open ChipScope Analyzer and start testing our links. PRBS31 and internal loopback make for an easy sanity check to make sure that your board is set up right, that clocks are running, and that power to the transceivers is correct. Great. All 4 lanes come up green. We have the correct 25.78 gigabit per second rate and report 0 errors. Now we can jump to external loopback and include the optical path. Many times it's useful to check an assortment of intermediate loopback configurations to gain confidence in each portion of the system, but we're skipping ahead and including the whole path. We can click on the external button for each link, which tells the receiver to receive the external serial data, which in this case is PRBS31 being transmitted from the FPGA through the Finisar CFP2, through 10 kilometers of fiber, back through the CFP2 and into the receiver. We can see that everything has come up and we have 0 errors with minimal tuning. That being said, sometimes debug is required. In these cases, iBert provides the ability to ease the pattern from PRBS31 to PRBS7 and tune the transmitter's precursor and postcursor. Receive equalization on our GTZ transceivers is auto-adaptive and is triggered by clicking that external button. Once there are no bit errors, we can move the data pattern back to PRBS31 and do some additional fine-tuning. One great tool to use at this point is iScan, which can show you the eye that the CDR is actually sampling from post-equalization. This can help you evaluate the margin and tune for maximized performance across operating conditions. All of this blue in the middle shows where we detected 0 errors, giving us lots of margin. iBert provides easy access to this functionality, as you can see here. Though since it's part of the GTZ transceiver itself, similar checks can be done in-system by any user design. Part of the reason we're seeing such excellent performance here is that the CFP2 modules contain retimers, which clock the data coming off the optical domain before retransmitting it into the FPGA. This has the effect of simplifying the implementation and bring up of the PCB as the optical and electrical domains are isolated from one another. Now that we have successfully evaluated the serial interconnect, we can take the optimized settings and use them in an actual design. In this case, we're using the Xilinx 100 gig Ethernet logic core connected to 4 GTZ transceivers, each running at the same 25.78 gigabit per second we tested in iBert. The data path still runs through the Finisar CFP2 module, but instead of looping the data back, we've connected it to the JDSU tester to check the validity of the traffic. What we've done is enabled the 100 gig Ethernet MAC IP to send random-sized packets to the JDSU tester. You can see here that we received a huge number of packets and had 0 errors. In the opposite direction, we can see that the JDSU box is sending packets, and here in the chip scope, we can see that the number of packets transmit matches what we've received. Again, no errors. What's impressive here is that not only are the 1s and 0s getting through, but that the whole system is working correctly, from the transceivers and the optics all the way into the Ethernet stack. Since the channel between the FPGA and the optics is within the OIF 28GB VSR specification, we are seeing great interoperability. We have performed similar tests with other CFP2 vendors and have seen great results across the board. With the 4 steps shown here, you can get your Virtex-7 design up and running with a CFP2 optical module utilizing the Xilinx Virtex-7 H580T, the world's first heterogeneous device. To learn more about the Xilinx 7 series FPGAs and the Virtex-7 HT family, please visit xilinx.com. Thank you for watching.